Hello students, welcome to IMS Gate Academy. In today's session, I am going to do certain number of the problems on the electronic devices and circuits. Already I explained in the first and second and third parts the number of formulas, how they to be derived also I explained now. By using those formulae, I will do these questions with now. And also before doing the questions, I want to do few more basics. What is thermal equivalent of voltage, how to find out that value, that formula will be given here now. And also the drift velocity versus electric field intensity, the curve I will give now. And also I will do diffusion length. After that Einstein relation also is there now. After that I will start the problems based upon this EDC gate questions now. So now, yes, we can start now. But I want to start with here with few basics only. That is thermal equivalent of the voltage I want to explain. Thermal equivalent voltage. It is denoted by letter Vt, thermal equivalent of voltage. Thermal equivalent of voltage depends upon temperature. The change of temperature changes thermal equivalent of voltage. Even in PN junction diode or even in semiconducting materials, even in BJT, we are going to use this thermal equivalent of voltage. So at any temperature, the equivalent voltage you can determine by using the formula I will give here now. The thermal equivalent of the voltage is denoted by symbol V suffix T. Thermal equivalent of voltage is denoted by symbol Vt. That Vt is calculated by Kt by Q. Kt by Q. K is nothing but Boltzmann's constant, Q is the charge, T is the temperature. The temperature must be in Kelvin, it must be there now. If you are given in the problem centigrade, you think it's so, you need to convert into Kelvin, then you can determine thermal equivalent of the voltage. Otherwise still easily K Boltzmann's constant and Q value, if you substitute it, mostly it comes like this now. Still we can write this formula in a simplified form. T divided by 11,600. 11,600. This formula you must use to find the thermal equivalent of the voltage. In the problem you will be given T equal to 300 Kelvin, Vt equal to how much? T equal to what now? 400 Kelvin. You need to find the Vt value, where T is the temperature in Kelvin. Kelvin we can write now, Kelvin. It's to be taken K only now. Kelvin only you must take now. So this formula is very important now. You must remember. Next point, I want to give one more. This is thermal equivalent of the voltage. If you want to find out means that will be useful. And still one more is required, the electric field intensity versus drift velocity. What now curve I want to give now. You can now graphical drift velocity versus electric field intensity. Electric field intensity. This curve I will give. So sometimes the gate is asking questions based upon this. This axis I have taken as a drift velocity Vd, because you will find problems based upon this. That is why I am giving drift velocity versus electric field intensity. Versus electric field intensity. The shape of this curve will be like this. It goes linearly initially. It goes linearly. Clearly I will draw, just wait. It goes linearly. Some shape of the curve is available here. Some shape of the curve you can find. Then after it goes straight, some shape of the curve is also available. That means up to some portion you can find linear curve, linearly it goes. Then after you can find parabolic shape, slightly it is a parabolic shape you can find up to this extent. This portion is a linear shape of the curve you can find. But here the some shape from here to here you can find parabolic. Parabolic. Then next it reaches to the what now? Saturation only now, constant. This is constant only now. It goes, it will remain constant. Constant only possible. Such a shape is mostly possible here now. Understand now. In this case, up to what extent of electric field intensity, it will be linear. Those values I will give. 0 to 10 power 3, 0 to 10 power 3, if you maintain this electric field intensity, it will be linear is possible now. After 10 power 3, 10 power 4, here you got it, means between 10 power 3 and 10 power 4 you can find the non-linear parabolic shape you can find. After 10 power 4, constant, electric field is going to remain constant only, we can say. Understand my point now. Anyhow, the electric field intensity will not be linear. Electric field intensity versus Vd will not be linear for any value. Up to some extent only you can find what now? Linear. Then after parabolic, then after constant only possible. Now, this is the drift velocity versus electric field intensity curve, I can say. Understand my point. Next one I will give. Next one more I want to give here now. What is Einstein relation? Einstein relation also required. EINSTEIN, Einstein relation. This Einstein relation formula also useful in doing certain number of the problems. What is that relation? That means a thermal equivalent of the voltage versus thermal equivalent of the voltage and the ratio of diffusion coefficient divided by mobility. That ratio you will get. I will give clearly, you can understand now. dN by mu n equal to the Einstein relation. dN by mu n equal to dP by mu p equal to thermal equivalent of the voltage. This is nothing but Einstein relation. Sometimes you will use some dP value and thermal equivalent of voltage. It comes necessity to find out the mobility of holes. Then you can use this formula. Or mu p will be given, Vt will be given, dP is required to determine. Then you can use only now. Understand me now. Anyhow, this is said to be Einstein relation. But if it, in the problems, will be useful, this formula also. This is Einstein relation. You must remember one, And one more last formula I want to give now. Then after I will start problems based upon this now. Diffusion length. Diffusion length. Diffusion length. But it is denoted by symbol L, diffusion length. The diffusion length may be possible due to electrons or holes. Anyone is possible now. That relation is taken in this way. Diffusion length formula is to be taken. For the holes, suppose I want to find LP square equal to dP into tau p into tau p into tau p. LP is nothing but first of all, LP equal to how much? Suppose you are asked, under root of dP into tau p. This formula is used. Diffusion length means, what is the meaning? When an electron is moving in extrinsic semiconductor, up to some period of the time, it will be in motion only. After some time, it is going to recombine with the hole. The recombination of the electron with the hole is said to be collision also, no problem. You can use that word. So we can write here now the distance covered by the electron, that's a mean free time of electron or hole in the semiconducting material, is said to be diffusion length only. Diffusion length means how long diffusion is done, how long it is done diffusion. Then after it is going to recombine only, you can say. Exact word we can write now. Exactly the definition we can give like this now. It is the average distance covered by charged particle only now, by a carrier. That carrier may be electron or hole. Before recombination only now. Before recombination, we can say that now. Before recombination, that is called as a diffusion length only now. For hole, you are going to, because where LP is nothing but the diffusion length, dP is nothing but, you know very well, coefficient of diffusion. Yesterday I explained coefficient of diffusion, we can write. Coefficient of diffusion we can write now. Tau p is nothing but mean free time of carrier. Mean free time of charge carrier only now. That carrier may be electron or hole only, we can say. The formula is applied for the what you can say holes only now. Suppose the diffusion length of electron, if you want to find for electron, you can find, this is for hole only now, for hole. For electrons, you can use this one. Electron, this is for hole. For holes only. Diffusion length for hole only now. I can write ln equal to under root of dn into tau n, I can write now. This formula you can use. But all these formulas are very, very important to do any sort of questions only now. But certain number of questions I will do, gate questions only I selected. I will explain by using this semiconductor topic I will do, because I give so many formulas in semiconducting materials now. Using them, I will give certain questions now. This is the first question. Anybody can tackle this question? Anybody can give answer for this question? Any student can give answer? It's a overgate question only now. But I want to wait for some time. You please try to message which option is correct from the given 4 options. Anybody? Any student can do this question without my help. You take time and message the solution. GATE 2023 given for 1 mark. What is given in a semiconductor? If the Fermi energy level lies in the conduction band, then semiconductor is known as. 4 options are given. Option A, degenerate N-type. Option B, degenerate P-type. Option C, non-degenerate N-type. D, non-degenerate P-type. Which option is correct? When we can say the given semiconductor is a degenerate semiconductor, when we can say it is a non-degenerate semiconductor, based upon the doping, based upon the type of the doping you made, type of the amount of the doping you made, perfect word, it's the right word, is nothing but the amount of the doping you made will help you to know whether it is a degenerative or otherwise non-degenerative. You can understand. I selected intrinsic semiconductor. It is a pure type of semiconductor. The doping is made, low level doping is made. When the low level doping is made, at the time we can call that semiconductor as a non-degenerative semiconductor. Low amount if you made, there is a non-degenerate semiconductor only now. In case doping is made more doping is made, heavily doped semiconductor we have here now. In that case, that semiconductor is said to be degenerate semiconductor. If the doping is made more, we are saying that as a degenerate semiconductor only now. But whether it is a N-type or P-type, how you can identify? When pentavalent atoms are doped more, you think it's so. Pentavalent atoms are doped more, you think it's so. At the time, what is going to happen now? It is said to be more concentration only, more amount of the pentavalent atom is a doped. More means it is a degenerate only now. But a pentavalent atoms you doped means it is an N-type extrinsic semiconductor. In degenerate N-type extrinsic semiconductor, the Fermi level is going to lie where? In the conduction band only. It is going to lie in the conduction band. It is lying on in the conduction band means we are saying that as a what not degenerate conduction band. What a degenerate N-type extrinsic semiconductor. In case you are doping heavily doped any intrinsic semiconductor, by trivalent atom, you think it's so. In that case, what is going to happen now? That is said to be degenerate P-type extrinsic semiconductor, heavily doped by what now? Trivalent atoms only now. At the time, it is a degenerate P-type only, we can say. In degenerate P-type, what you can find? The Fermi level is going to exist in the valence band only now. If it is lying in the valence band, we are saying a P-type. If it is lying in the conduction band, means it is a N-type, it is a degenerate only now. Sorry, degenerate N-type only. Now you identify it is a non-degenerate or degenerate. In a semiconductor, the Fermi level here directly given, Fermi level here given clearly. I will give clearly. Here clearly specified here now. What is specified? The Fermi energy level lies in the conduction band is given. The Fermi level is lying in the conduction band means it is a N-type and also degenerate. Lying in the conduction band indicates Degenerate n-type only possible. So, which option is correct means option A is correct. Understand? There is a degenerate n-type extrinsic semiconductor. I think you followed. Yes, I will go to next question. This is a GATE 2023. It was given for 1 mark. Next question. You try this question. I will give in your hand. Next question. You please try this question. This is also GATE 2023 1 mark question. I will see how many number of students can give answer for this question. Start doing this question without my help. Start doing this question. Anybody? Anybody can give answer for this question. But in this problem, it is given like this. Just I will read out this question, then after I will explain. For an intrinsic semiconductor at temperature T equal to 0 Kelvin, which of the following statement is true? What he says, the type of semiconductor is an intrinsic semiconductor, clearly given. It is an intrinsic semiconductor. But temperature is maintained 0 Kelvin. This temperature is 0 Kelvin only now. So, which option is correct? What are the 4 options are given? Option A. All energy states in the valence band are filled with electrons and all energy states in the conduction band are empty of electrons. All energy states in the valence bands are filled with electrons means all the electrons are in the valence band, he says. All the electrons are in the valence band and conduction band are empty of electrons. That means conduction band does not have any number of electrons, he says in the problem. That means electrons are in the valence band, no electrons in the conduction band. That is the first option. Second option, all energy states in the valence band are empty of electrons and all energy states in the conduction bands are filled with the electron. Second option says conduction band is fully filled with the electron and valence band is empty, he says. Second one. Third one, all energy states in the valence and conduction bands are filled with holes. Valence band and conduction band are filled with holes only, he says. All energy states in the valence and conduction bands are filled with the electrons, option D. Valence band and conduction band are filled with the electron, he says, option D. Which option is correct? You catch my point. It is an intrinsic semiconductor, temperature is maintained 0 Kelvin. So, intrinsic semiconductor at 0 Kelvin can act as an insulator only. It can act as an insulator. It does not conduct. It does not have any number of electrons in the conduction band. All the number of electrons are existing in the valence band only now. Why the conduction is not done means no electrons are there in the valence band, in the conduction band. No electrons are there in the conduction band. All the electrons are in the valence band. If no electrons are there in the conduction band means what happens now? It doesn't. You cannot find any conduction of no conduction possible because no electrons in the conduction band. That's why we can write one point at solution. We can write like this now. At T equal to 0 Kelvin, at T equal to 0 Kelvin, intrinsic semiconductor acts as insulator. That is very important. Acts as insulator. It is acting just like an insulator only. Why? Reason is what means because acts as insulator, because reason is what? Because no electrons, no electron means empty only now, no electrons, no electrons in conduction band, no electrons in conduction band. That means conduction band is empty, no electrons in conduction band. But otherwise, and valence band is filled with electrons only. All the electrons are in the valence band only, and valence band is filled with electrons, we can say filled with electrons. This is only condition. As per this point, we can say option A is correct. All energy states in the valence band are filled with electrons. That means valence band filled with electrons only. And energy states in the conduction band are empty. Conduction band are empty of electrons only possible. That's why option A is correct only, we can say. It is a GATE 2023 given for 1 mark. Easily students can get these marks only now. Next problem. This is one more question. I will see how many number of students can do this question. I want to give in your hand just to try this question and give your answer. You take time and try to solve these questions to give this answer. Can you complete this question? Anybody? Anybody can do? Anybody can do this question without my help? I want to check how many number of students can do this question without my help. I will compare with my answer. Anybody? Yes, I will do, please watch. It is also GATE question only now. I think GATE 2023, I think this question also 23 or 22, sorry, 23 or 22, sorry. In an extrinsic semiconductor, the whole concentration is given to be 1.5 times of Ni. Ni means you know very well, intrinsic concentration, where Ni is the intrinsic carrier concentration of 1 into 10 power 10 per cm cube. Intrinsic concentration value is given in the problem. The ratio of electron to hole mobility for equal hole and electron drift current is given as dash, round off to 2 decimal places. Is asking to find the ratio of electron to hole mobility. What is given in the problem? The hole concentration is given to be 1.5 times of Ni. Hole concentration is given. Hole concentration I can put P. P I can put here now. The whole concentration P is given as, the P is given as 1.5 times of Ni. 1.5 times of Ni is given, whole concentration. But where Ni equal to here given 1 into 10 power 10 per cm cube, 1 into 10 power minus 10 power 10 per cm cube. I can put Ni equal to here given 1 into 10 power 10. Directly I can write 10 power 10 per cm cube. This Ni value I can substitute in the above equation to get concentration of holes. I can write concentration of holes equal to 1.5 times of Ni. Ni is nothing but 10 power 10. This is the concentration of holes here possible. In extrinsic semiconductor, hole concentration is given by that much given hole. Stand up. But in the problem is asking to find ratio of electron to hole mobilities. Is asking to find mu n by mu p equal to how much? That means electron ratio of electron to hole mobility EOS. At what condition we need to calculate this value? For equal hole and electron drift current, at this condition I want. That means electron drift current and hole drift currents are equal, means I want this ratio. What he says here now is the current due to electrons, current due to holes, current due to the electrons, that is due to drift. is equal to current due to the holes, that is also due to drift, are equal. When these two drift currents are equal, I want mu n by mu p only now. But what is the formula we need to use for ion drift and IP drift? Ion drift and IP drift is calculated by the formula. I will give now, clearly you can understand this formula onwards. This is given as P into, for electron if it is required, N into Q into mu n into E into A. Current density equal to, you know very well, sigma into E. Sigma is nothing but conductivity N into Q into mu n into electric field, current density. Current means multiply by A. IP drift means what you have to do? P into Q into mu P into E into A. That's possible. This is the current due to holes because of the diffusion only we can say. On both sides I can cancel Q into E into A, Q into E into A. Finally, what I got? N into mu n, that is equal to P into mu P. P into mu P I can write now. But what ratio is required here now? Mu n by mu P is required. That ratio I can get from P by N. P by N. We know concentration of holes P. We don't have an idea about the N concentration. By using the mass action law, I can find N. I can say N is calculated by mass action law. Ni square by P I can use. Ni square, Ni is at 10 power 10, 10 power 10 whole square, 10 power 20 I can put here now. Divide by P. P is nothing but 1.5 into 1.5 into 10 power, 1.5 into 10 power 10. This can be written as about 10 power 10 divided by 1.5 I will get. 10 power bases are equal means powers 20 minus 10. I can put 10 power 10 by 1.5. Now I can substitute here now. The P is nothing but 1.5 into 10 power 10 divide by N. N is nothing but 10 power 10 divided by 1.5. 1.5 goes to numerator. 10 power 10, 10 power 10 here cancel. Finally, mu n by mu p can be taken as a mu n by mu p is taken as 1.5 into 1.5. How much? 2.25 mostly I think now. It comes as a 2.25 only now. That value is a 2.25 mostly it is possible. 2.25 is possible. Yes. This is the solution for this question. In that way, we can get answer right now. So, how the formulas are useful from the semiconductors? I gave this now. This is one of the example. I hope you followed this. And I want to give one more question. You please try. You please try this question without my help. It's a GATE 2017 problem. I'll see how many number of students can do. You start doing this question. It's a 2 marks question. I'll see who are those students are going to give answer for this question. Please give it. I am waiting for your answer. Anybody? Anybody can do this question? What is given in this problem? The dependence of drift velocity of electrons on electric field in a semiconductor is shown below. But how the drift velocity is dependent upon the what now? Electric field intensity is given by this graph. The semiconductor has a uniform electron concentration of N equal to 1 into 10 power 16 per cm cube. That many number of electrons are existing. and electric charge Q equal to 1.6 into 10 power minus 19 coulombs given. If a bias of 5 voltage is applied across 1 micrometer length of this semiconductor, the resulting current density in this region in kiloamperes per cm square is dash is given. What graph is given in the problem? This is a drift velocity. Y-axis is nothing but the drift velocity is given here now. X-axis is nothing but the electric field is given here now. Volts per centimeter is a centimeters per second. Up to some portion, we are finding this curve linear only. Up to this 5 into 10 power 5, it is given linear curve only now. Then after it is given constant. Then after it is given constant. The curve shape is given like this. But what is given and what he is asking in the problem, that we can see. But I want solution for this question. The dependence of the drift velocity is, but the semiconductor has a uniform electron concentration. Concentration of electrons here given. N equal to 10 power 1 into 10 power 6 means 10 power 16 per cm cube is given. With the concentration of electron 10 power 16. Charge is given, we know very well. Supply voltage V is given 5 voltage. If this semiconductor is connected by voltage source 5 volts, voltage is given 5 volts. 5 volts is given. Is applied across a 1 micrometer region of this semiconductor. The length of the semiconductor is given. Length I can take L or X. I have taken X for example. X is the length of the semiconductor is given as a 1 micrometer. 1 micrometer. But I wish to get with units of centimeters. So, micro equal to 10 power minus 6. Meters, if you convert it into the centimeter now, 10 power 2, 10 power minus 6 into 10 power square is nothing but 10 power minus 4 centimeters possible. 10 power minus 4 centimeters length of the semiconductor instead now given. And what is asking, the resulting current density is required. Resulting current density means J value how much is asking. That is required in kiloamperes per cm square is given, per cm square. With that units I want, that is required. How we can measure? In the problem it is given clearly. When electric field intensity, this is a E1 I can assume. Intensity E1 equal to 5 into 10 power 5. Drift velocity 1, VD1 is given 10 power 7 centimeters per second. This is a linear only. E1 is given here. E1 equal to 5 into 10 power 5. 5 into 10 power 5. 5 into 10 power 5 volts per centimeter. At this intensity, drift velocity is given 10 power 7. What units? Centimeters per second. Centimeters per second it is given. VD1 value. But I want concentration is this much, voltage is this much, this length of the semiconductor is at 10 power minus 4. You find out J value. J equal to how I can get here now? Current density is calculated by sigma into E. We know very well. Sigma into E. Generally you will apply. What is sigma? N into Q. It is a concentration of electrons. N into Q into mu N. N into Q into mu N is given here now. N into Q into mu N. Is it given mobility of electrons or not in the problem? Electron, the semiconductor N equal to given, Q is given, voltage is given, the resulting current density is asking to find. Okay, sigma into E. Electric field intensity equal to, you know very well, electric field intensity is, that is E I am putting here now. Mobility is not given in the problem to find directly. But mu N into E is nothing but, this is already E1 is there, this intensity E2 I will put now. At the concentration of 10 power 16, N equal to that much concentration, electric field intensity is E2 only now. But mu n into E2 is nothing but drift velocity. I can write again. NQ into mu n into E2 is nothing but drift velocity 2. If I know very well VD2 value, J value I can calculate. Concentration of electrons given, charge we know, VD2 if you got, directly you can get J value. But how to get that VD2 is very important now. The VD2 versus intensity, VD2 and E2 are here given relation here now. First of all, what is E2? I want to find. Electric field intensity is nothing but voltage by distance. Voltage is given 5 voltage. When the voltage is connected 5 voltage, the length of the semiconductor is at 10 power minus 4. I want current density. This is nothing but 5 into 10 power 4. That much volts per centimeter I got. Volts per centimeter. 5 into 10 power 4 means I want what is VD2. At this electric field intensity, I want what is VD2 equal to how much? But 5 into 10 power 4 means it comes below this E1. E2 will be below E1 only, below E1 only. Corresponding value will come below. On this linear curve only it comes, on this linear curve. When it is in linear, I can write one relation. What relation I can put here now? VD2 by relation I can form. VD2 by VD1 equal to E2 by E1 relation I can form. Equal to why it is taken? It is a linear only now. But a VD2 is directly proportional to intensity possible. Proportionally constant for both equal. We can cancel now. And I wish to find what is VD2. If I know the VD2, I can get answer. How I can get VD2? VD2 is nothing but VD1 10 power 7. 10 power 7. VD1. E2 is nothing but 5 into 10 power 4. 5 into 10 power 4. Divided by VD2 by E1 is possible. Divided by E1. E1 is nothing but 5 into 10 power 5. Use calculator, you will get answer only now. Then you will get what is VD2. What VD2 you can get? Its value will be like this now. I will give 5 into 10 power 4, 10% of 5 into 10 power 5. It comes as 10 power 6 it comes, because 5 cancel, and also 10 power 5, 10 power 6 is possible mostly. 10 power 6 it comes. 10 power 6 centimeters per second it comes now. Centimeters per second. But I want this VD2, whenever you are getting, you can determine what is J. J is nothing but N into concentration of electron 10 power 16 it is given. 10 power 16 is given. N into Q is nothing but 1.6 into 10 power 1.6 into 10 power minus 19 into VD2. VD2 is nothing but 10 power 6. You can multiply 10 power 6. But finally, the value will be 1.6 kilo amperes. 1.6 kilo amperes per cm square is possible. Per cm square is possible. Like that, you can determine current density. I think you followed perfectly this question. 1.6 kilo amperes per cm square. This is one more good question. 2017 I can give. Now I wish to give one more question in your hand. By using the semiconductor formula, you can try these questions. Yes, this is one more problem. Yes, anybody can tackle this question, the gate question asked in 2015. You please try it. Can you try this question without my help? You please try this. Anybody can do this question? What is given in the problem? A piece of silicon is doped uniformly with phosphorus. A piece of silicon is doped uniformly with phosphorus is given. Phosphorus is a pentavalent or trivalent atom. That impurity is said to be pentavalent only now. At the time, what concentration is going to increase? Electrons concentration is going to increase only now. A piece of silicon is doped uniformly with a phosphorus with a doping concentration 10 power 16 per cm cube. There the donor concentration is given in the problem. Nd is given in the problem. Nd is nothing but 10 power 16 per cm cube, 10 power 16 per cm cube. The expected value of mobility versus doping concentration for the silicon assuming full dopant ionization shown in the figure. In the diagram, one graphical figure is given. Doping concentration on x-axis, and this axis is a mobility. Doping concentration versus mobility only given here now. And the charge of electron is 1.6 into 10 power minus 19. We know very well that point. The conductivity in Siemens per centimeter of the silicon sample at 300 Kelvin is dash. That is the question. Is asking to find the conductivity. Conductivity is nothing but, in the last class I explained, the charge density into mobility is nothing but conductivity, already given. Charge density is nothing but NQ into mu n. Only. But here the N is, but in the N-type X, it is a pentavalent atom is a doped. When pentavalent atom is doped, the concentration of electrons N is approximately equal to Nd only now. That means in N-type extrinsic semiconductor, N is approximately equal to Nd. Donor concentration and total concentration is approximately equal. So I can write this conductivity is nothing but Nd into Q into mu n, I can put here now. But in this problem, mobility is not given. By finding this mobility, you can get the required value. Nd value we know, Q we know, mu n is required. But in the problem it is given the donor concentration is nothing but 10 power 16, 1 into 10 power 16. 1 into 10 power 16 we got where? 1 into 10 power 16 is this only given, this point. 1 E plus 16, E plus 16 means 10 power 16 only now. Corresponding to this doping concentration, we need to find when you extend that line this side, where it is intersecting the curve, you watch it now. This is intersecting here only. Because given 1E into 1E plus 16 is given. 1E plus 16 is nothing but 10 power 16 donor concentration. Corresponding to this mobility is nothing but 1200 volts per cm square per volt second only. This is the mobility value. Mobility of what? Electrons only here given. I can take from the table, I got 1200 here now. The mu n is nothing but 1200 cm square per volt second, I can put here now directly. Now these values we can substitute now. Sigma equal to, I can write donor concentration, I got 10 power 16. The charge Q is nothing but 1.6 into 10 power minus 19. And mobility of electrons given 1200 here now. Use calculator, you will get answer, sigma. That value is, that is given as a, I will give the value. 1.92 Siemens per second. Otherwise mho per second, mho per centimeter, or otherwise Siemens per centimeter you can say. This is the solution for this question only now, 1.92. This answer I can put 1.92 directly. That is answered. It's a GATE 2015 question window. I hope you followed so far. Thank you.